Hello there, and welcome to After Dark Space, where the biggest questions about space and science and the human story within it are explored at the pace of a slow breath, where curiosity is never rushed, and where the universe unfolds one careful thought at a time. Tonight, we are going to follow something small, smaller than you might expect, given how large the questions surrounding it tend to grow. We are going to follow a machine the size of a small car, built in the 1970s, launched when most of the technology you use every day did not yet exist, and now traveling through a region of space no human-made object had ever entered before it arrived there. We are going to spend tonight with Voyager 1, with its story, its trajectory, its science, its silence, and the extraordinary, almost unbearable truth that it will drift through the darkness between the stars essentially forever, long after every trace of the civilization that built it has disappeared from the universe entirely. This is not a sad story, or rather, it is not only a sad story. It contains within it some of the most moving and most meaningful things that have happened in the entire history of our species, and sitting with it carefully without rushing past the parts that require patience tends to change something about how the night sky feels when you look up into it afterward. Before we begin, I want to ask where you are tonight. Perhaps you are lying in the quiet of your room, the outside world dimmed and distant. Perhaps you are on a couch with a blanket gathered close, the evening doing what evenings do when they are allowed to settle properly. Wherever you are approximately the same distance from a warm star as Voyager 1 was when it was launched in 1977. And in the decades since, it has traveled farther from that star than any object our species has ever intentionally sent anywhere. It is, right now, as you read or listen to these words, the most distant human-made object in the universe. If this kind of careful, unhurried exploration of space and what it means helps your mind settle into rest, it would mean a great deal if you tapped the like button or subscribed to After Dark Space. It helps other people who need a quiet voice to think alongside find their way here. Now, let your body settle into where it is. Take one slow breath in and let it out without any urgency at all. And let's begin. Let's start with the simplest possible version of the problem, stated as plainly and as honestly as physics and engineering allow. Mars is approximately 225 million kilometers from Earth when averaged across both planets' elliptical orbits, though this distance varies enormously depending on where both planets are in their respective orbits around the Sun. At their closest, the two planets come within about 54 million kilometers of each other. At their farthest, they are separated by more than 400 million kilometers. A mission to Mars is, by necessity, planned around the orbital dynamics of this varying distance, launched during specific windows, called launch opportunities or opposition windows, when the alignment of the planets makes the journey as efficient as possible. The journey itself, using the most efficient trajectories available to currently conceivable spacecraft, takes between 6 and 9 months each way, depending on the specific trajectory chosen and the technology used. A mission that departs Earth during one launch window, travels to Mars, conducts operations on the surface, and then waits for the next suitable launch window to return, would require a total duration of somewhere between 18 months and 3 years from departure to homecoming. Some mission architectures compress this, some extend it. But no realistic scenario, using physics that actually exists rather than physics that has been imagined for science fiction, makes the round trip substantially shorter than this. This is already a long journey by any human standard. The longest single continuous space mission on record, as of the mid-2020s, involves stays of roughly 1 year aboard the International Space Station. And those missions occur in the relative proximity of low Earth orbit, where emergency return is possible within hours and where communication with Earth involves no meaningful delay. Mars is neither of these things. Emergency return from Mars is not possible within hours or days or even weeks, and communication with Mars because light itself takes between 3 and 22 minutes to travel the varying distance, means that every transmission, every request for help, every report of a problem, every acknowledgement of a solution arrives at a significant delay in each direction. Real-time conversation is physically impossible. Every decision made on Mars must ultimately be made by the people who are on Mars. So the journey is long. The return window is constrained by orbital mechanics, and the people on the surface are, in a genuinely important sense, truly on their own. This is the basic physical situation before we have even begun to address the biological challenges, the psychological challenges, the engineering challenges, or the existential dimension of what such a journey would mean for the human beings who undertake it. The return problem deserves its own careful unpacking because it is more complicated than it might initially appear, and because understanding it fully is essential for appreciating the honest statement in tonight's title. Returning from Mars requires a rocket capable of lifting a crew and their return vehicle off the Martian surface, escaping Mars's gravitational pull and conducting a months-long journey back to Earth. Mars's surface gravity is roughly 38% of Earth's, meaning that while its gravity is weaker than Earth's and requires correspondingly less energy to escape, it is not negligible. A return vehicle launched from Mars still needs to achieve significant velocity to escape the planet, roughly 5 kilometers per second to reach escape velocity, compared to Earth's 11 kilometers per second. But this rocket, this return vehicle, with all its fuel and all its life support and all its systems, has to either arrive at Mars before the crew does, having been sent ahead on a previous mission, or it has to make the 6 to 9 month journey with the crew, consuming resources during the outward trip as well as the return. In either case, the mass involved is enormous. Rocket fuel is heavy. Life support systems are heavy. The engineering required to get any significant mass off the Martian surface is substantial, and every kilogram that has to be lifted off Mars has to have been landed on Mars first, which means it had to be transported from Earth, which means the mass launched from Earth is dramatically larger than the mass that eventually lands on Mars due to the fuel consumed during the transit. Every additional kilogram of return fuel requires additional departure fuel, which requires additional fuel for that fuel in the cascading arithmetic of rocketry known as the rocket equation, which punishes mass with exponential ferocity. This is why returning from Mars is harder than going to Mars. Going to Mars requires getting to Mars. Returning from Mars requires getting to Mars and then getting back, which means carrying the capability to do the return trip during the outward journey, which means carrying far more mass than a one-way mission would require. The numbers are formidable. Not impossible, but formidable. Every serious engineering study of Mars missions has identified the return journey as one of the central, most challenging, most expensive aspects of the entire enterprise. And here is the specific implication for the first crewed Mars missions. If the return capability fails, for any reason, at any stage of the mission, the people on Mars are not coming home. If the return vehicle is damaged during landing, if a fuel system malfunctions, if the launch window passes during an unresolvable technical emergency, if the life support on the return vehicle fails during the months-long journey home, if the navigation systems fail during approach to Earth. At any of these points, and at many more besides, the people who went to Mars are the people who die on Mars, or in the space between. This is not a scenario invented for dramatic effect. It is an honest assessment of what it means to undertake a mission to another planet at the current level of our technological capability. Before we go further, let's spend some time with the people who might actually go, because any honest exploration of this subject has to honor the human reality of it rather than treating the crew as abstract variables in an engineering problem. The people who will travel to Mars first will not be drafted. They will be volunteers, and by all accounts of those who study the psychology of extreme exploration and those who have already expressed willingness to go, they will be volunteers who understand perfectly well what they are signing up for. The history of exploration is full of people who chose, deliberately and with open eyes, to go somewhere extraordinarily difficult and extraordinarily dangerous, knowing that return was not guaranteed and accepting that risk as the price of the extraordinary thing they were choosing to do. Ernest Shackleton's famous advertisement for Antarctic expedition crew, whether the specific wording is historically accurate or somewhat legendary, captures something true about the psychology of extreme explorers. Hazardous journey, small wages, bitter cold, long months of complete darkness, constant danger, safe return, doubtful, honor, and recognition in case of success. People answered that advertisement. People have always answered that advertisement in every era and every culture when the call goes out for those willing to go somewhere genuinely difficult and genuinely unknown. The astronauts and cosmonauts who have flown to orbit already understand something of this calculus. Every launch carries risk. The history of human spaceflight includes 14 people who died during missions aboard Challenger and Columbia, and 3 who died in the Apollo 1 fire on the launch pad. Every person who straps into a spacecraft does so understanding, at least abstractly, that the vehicle might not bring them home. But Mars raises this calculation to a different order of magnitude because the distance is so much greater, the journey so much longer, the rescue so much more impossible, and the window for return so much more constrained. People who study the psychology of long-duration isolation and exploration have thought carefully about what kind of person can sustain years of confinement in a small space, separated from everything familiar, facing genuine daily danger, and performing high-stakes technical work while doing so. The characteristics identified tend to include emotional stability, high tolerance for uncertainty, strong collaborative instincts combined with genuine individual competence, the ability to find meaning in the work itself rather than in external validation, and a particular relationship with risk that is neither reckless nor paralyzing. These are not common characteristics. They describe a specific kind of person. And among those people, a subset will emerge, in whatever era the first Mars mission becomes possible, who look at the distance and the danger and the possibility of never returning and decide that going is worth more to them than staying. The question of what it means for a human being to make that decision with full knowledge of the probability distribution of outcomes is one of the more interesting and more important questions this topic raises. Let's think carefully about what the one-way possibility would actually mean in practice, because it is easy to speak of it abstractly, but considerably harder to hold clearly in the mind. Imagine being selected for the first crewed Mars mission. You have spent years preparing, training for the specific physical and technical challenges of the journey and the surface. You know the timeline: 6 to 9 months of travel in a confined spacecraft, then surface operations for whatever duration the mission calls for, then a wait for the return window, then months more of travel home. You know that the return depends on systems that have never been tested in exactly these conditions, on fuel that has been sitting in a tank on another planet for however long since it arrived, on a rocket that has been exposed to Martian radiation and temperature cycles and dust storms for the duration of your stay. You know that if any of these things fail catastrophically enough, you are not going home. How do you live with that knowledge? The answer, from the psychology literature on extreme exploration and from conversations with astronauts and with the people who support them, is that you compartmentalize it to some degree. Not by denying it, but by acknowledging it fully and then choosing again to proceed. The knowledge of the risk is integrated into the identity of the explorer rather than sitting outside it as a threat. The person who goes to Mars first will have, in some sense, already accepted the possibility of not returning, not as a resignation to fate, but as a conscious, considered choice that the experience of going is worth more than the guarantee of coming back. This kind of choice has analogues throughout human history, even if none of the analogues are perfectly precise. The sailors who crossed uncharted oceans in wooden ships did not have guaranteed return. The early aviators who pushed the boundaries of what aircraft could do did not fly with guaranteed survival. The mountaineers who pushed into the death zone on the world's highest peaks knew that altitude and weather and the limits of human physiology could conspire to keep them there permanently. In each case, the people who chose to go did so with some version of the same understanding. The thing at the end of the journey is worth the risk that you might not come back from it. What makes Mars different from all of these analogues is the scale of the distance and the permanence of the isolation. A sailor who runs into trouble in uncharted waters is still on the same planet as the people who might eventually find them. A mountaineer who turns back from the summit is an hour or a day or a week from base camp and eventually from civilization. A person stranded on Mars is 225 million kilometers from the nearest other human beings, separated by a journey that takes months even under optimal conditions, in a place where no search and rescue has ever occurred, and where the idea of rescue, at least with anything resembling current technology, is essentially fiction. This is not a metaphor for isolation. This is a new kind of isolation that the human species has never actually experienced before, even in all the long history of exploration and adventure and deliberate, dangerous choice. Hello there, and welcome to Beyond the Cosmos, where the biggest questions about space and science and the human story within it are explored at the pace of a slow breath, where curiosity is never rushed, and where the universe unfolds one careful thought at a time. Tonight, we are going to follow something small, smaller than you might expect, given how large the questions surrounding it tend to grow. We are going to follow a machine the size of a small car, built in the 1970s, launched when most of the technology you use every day did not yet exist, and now traveling through a region of space no human-made object had ever entered before it arrived there. We are going to spend tonight with Voyager 1, with its story, its trajectory, its science, its silence, and the extraordinary, almost unbearable truth that it will drift through the darkness between the stars essentially forever, long after every trace of the civilization that built it has disappeared from the universe entirely. This is not a sad story, or rather, it is not only a sad story. It contains within it some of the most moving and most meaningful things that have happened in the entire history of our species, and sitting with it carefully without rushing past the parts that require patience tends to change something about how the night sky feels when you look up into it afterward. Before we begin, I want to ask where you are tonight. Perhaps you are lying in the quiet of your room, the outside world dimmed and distant. Perhaps you are on a couch with a blanket gathered close, the evening doing what evenings do when they are allowed to settle properly. Wherever you are approximately the same distance from a warm star as Voyager 1 was when it was launched in 1977. And in the decades since, it has traveled farther from that star than any object our species has ever intentionally sent anywhere. It is, right now, as you read or listen to these words, the most distant human-made object in the universe. If this kind of careful, unhurried exploration of space and what it means helps your mind settle into rest, it would mean a great deal if you tapped the like button or subscribed to Beyond the Cosmos. It helps other people who need a quiet voice to think alongside find their way here. Now, let your body settle into where it is. Take one slow breath in and let it out without any urgency at all. And let's begin. To understand what Voyager 1 is and why it matters so much, we need to begin at the beginning, in the mid-1970s, when a remarkable alignment of planetary positions presented human beings with an opportunity that will not recur for another century and a half. Every few decades, the four outer planets of the solar system, Jupiter, Saturn, Uranus, and Neptune, align in a configuration that makes it possible, using the gravitational assistance of each planet, to accelerate a spacecraft onward to the next, to visit all four worlds in a single mission. A journey that would otherwise be far beyond the capability of the propulsion systems of the era, or, frankly, of most eras since. This alignment, called the Grand Tour opportunity by the scientists who identified it, was studied in the late 1960s by a researcher at NASA's Jet Propulsion Laboratory named Gary Flandreau, who recognized that a spacecraft launched in the 1977 to 1978 window could use Jupiter's gravity to slingshot toward Saturn, Saturn's gravity to slingshot toward Uranus, and Uranus's gravity to slingshot toward Neptune, all within a single mission lasting roughly 12 years. The recognition of this opportunity was the spark that eventually became the Voyager program. NASA initially planned an ambitious Grand Tour mission involving 4 spacecraft visiting all the outer planets. Budget constraints reduced this to a more modest pair of spacecraft, each weighing roughly 825 kilograms, equipped with instruments designed to study the planets and their moons, their magnetic fields, their atmospheres, and the space environment through which they traveled. Voyager 1 and Voyager 2 were launched within weeks of each other in the summer of 1977. Voyager 2 on August 20th and Voyager 1, despite its name suggesting it launched first, on September 5th. Voyager 1 was placed on a faster trajectory that would allow it to reach Jupiter and Saturn sooner, while Voyager 2 followed a different path that would eventually take it on to Uranus and Neptune, completing the full Grand Tour that budget constraints had made impossible to accomplish with a single spacecraft. The technology aboard each Voyager was, by the standards of 1977, sophisticated, and by the standards of today, almost impossibly primitive. The computer systems aboard Voyager 1 have roughly 68 kilobytes of memory in total, a quantity so small compared to modern computing that most comparisons strain credibility. The smartphone in your pocket likely has several million times more computing power than the device currently traveling through interstellar space at 61,000 kilometers per hour. And yet, the mission has worked. Decades after launch, the spacecraft's systems, most of them, continue to function, and the data it sends back continues to reveal things about the universe that no other instrument has ever been positioned to observe. The journey of Voyager 1 through the outer solar system, from its launch in 1977 through its encounters with Jupiter and Saturn, is worth spending time on. Not merely as historical context, but because those encounters shaped everything that followed, both scientifically and in terms of the trajectory that would eventually carry the spacecraft into interstellar space. Jupiter loomed first, and Voyager 1's closest approach to the giant planet occurred in March 1979. What the spacecraft's cameras and instruments revealed rewrote the textbooks on planetary science in a single encounter. The storms of Jupiter had been observed telescopically from Earth for centuries, and the Great Red Spot, a storm larger than the entire Earth that has been raging for at least hundreds of years and possibly much longer, was already famous before Voyager arrived. But the images returned by Voyager revealed Jupiter's atmosphere in a detail and a dynamism that no previous observation had captured: swirling bands of cloud, complex interactions between weather systems, turbulence and color and structure at every scale. The moons were perhaps even more revelatory. Io, Jupiter's innermost large moon, was discovered to be the most volcanically active body in the solar system, its surface continuously reshaped by hundreds of active volcanoes driven by the extraordinary tidal forces exerted on it by Jupiter's gravity. Images of active volcanic plumes rising hundreds of kilometers above Io's surface were among the most stunning images returned by any space mission to that point. Europa, another of Jupiter's large moons, was revealed to have a surface of smooth, cracked ice that suggested the presence of a liquid water ocean beneath, an ocean that subsequent missions would confirm, and that remains, to this day, one of the most promising locations in the solar system for the possible existence of extraterrestrial life. From Jupiter, Voyager 1 was flung outward by the planet's gravity and redirected towards Saturn, which it reached in November 1980. Saturn's rings, already known to be complex but observed only at the limited resolution available from Earth, were revealed by Voyager to be structures of extraordinary intricacy, composed of countless individual ringlets, some of them braided and twisted in ways that orbital mechanics theory did not immediately explain. The Moon Titan, Saturn's largest, drew particular attention because it had been known to possess a thick atmosphere, unusual for a moon, and Voyager's close pass revealed a world shrouded in an opaque orange haze, hiding a surface that would remain unknown until the Cassini-Huygens mission of the 2000s. The decision that ultimately determined the rest of Voyager 1's trajectory, and thus its eventual destiny as the most distant human artifact in the universe, was made during the Saturn encounter. Scientists had the option of directing Voyager 1 on a path that would carry it past Titan for a close examination of that mysterious moon, or directing it on a different path that would have preserved the option of continuing to Uranus and Neptune as Voyager 2 was able to do. Choosing Titan meant choosing a trajectory that bent the spacecraft upward out of the plane of the solar system, away from the remaining planets and onto the path it has followed ever since, outward and upward into the darkness beyond anything the solar system's planetary family contains. The choice was made. Titan was prioritized, and from November 1980 onward, Voyager 1 has been heading in only one direction: away. The concept of the heliosphere is central to understanding where Voyager 1 has gone and what it has found there. So let's spend some careful time with it before we follow the spacecraft farther into the dark. The Sun is not a static object sitting quietly in the center of the solar system while the planets orbit around it. It continuously emits a stream of charged particles, primarily protons and electrons, flowing outward in all directions at speeds of several hundred kilometers per second. This stream of particles, called the solar wind, permeates the entire volume of space that we typically think of as the solar system, extending outward far beyond the outermost planets, carrying with it a magnetic field generated by the Sun's own internal dynamics. The vast bubble of space within which the solar wind dominates the local particle and magnetic field environment is called the heliosphere, and it represents, in a very real sense, the sphere of direct physical influence of our particular star. The heliosphere is not a perfect sphere. It is shaped by its motion through the interstellar medium, the sparse gas and magnetic field that fills the space between the stars in our galaxy. As the solar system moves through this medium, the heliosphere is compressed in the direction of travel and extended in the trailing direction, like a bubble being pushed through water, elongated on the downstream side. Its exact dimensions are not perfectly known, but it is generally thought to extend to somewhere between 100 and 200 astronomical units from the Sun, where 1 astronomical unit is the average distance from the Earth to the Sun, roughly 150 million kilometers. Beyond the heliosphere lies the interstellar medium, the ancient, sparse, faintly structured gas and magnetic field that predates the solar system, that was here before our Sun formed, and that will remain when our Sun has long burned out. The boundary between the heliosphere and the interstellar medium is called the heliopause, and crossing it represents, in a physically meaningful sense, leaving the domain of the Sun and entering the domain of the galaxy. Voyager 1 crossed the heliopause in August 2012, becoming the first human-made object to enter interstellar space. This crossing was not immediately obvious from the data because the heliopause is not a sharp boundary with a clearly posted sign. It took months of analysis before the scientific team was confident enough to announce in September 2013 that the crossing had occurred. The evidence came from changes in the particle environment around the spacecraft, a dramatic drop in the intensity of particles from the solar wind, and a corresponding increase in cosmic ray particles from outside the solar system, and from changes in the local plasma environment that confirmed the spacecraft was now swimming in a different medium than the one it had moved through for the preceding 35 years. The moment of crossing, even experienced retrospectively through data, carried a weight that scientists and laypeople alike found deeply moving. A machine built by human hands had, for the first time in the history of life on Earth, departed the immediate physical influence of the Sun and entered the wider galaxy. It had crossed a threshold that represents, in a very real sense, the beginning of everything that is not the solar system. Let's think carefully about the numbers involved in Voyager 1's journey, because they are almost impossibly large by everyday standards, and the effort to hold them in the mind produces something important about the relationship between human scale and cosmic scale that is worth sitting with. As of the mid-2020s, Voyager 1 is roughly 24 billion kilometers from Earth. Let's try to give that number some texture, because 24 billion is a quantity that resists direct mental engagement. Light, traveling at approximately 300,000 kilometers per second, takes about 22 hours to cover the distance between Voyager 1 and Earth. This means that when the spacecraft's controllers at the Jet Propulsion Laboratory send a command to Voyager 1, they wait 22 hours for the signal to arrive. And then they wait another 22 hours for any response to return. Nearly 2 days pass between asking a question and receiving an answer. Every interaction with the most distant object our species has ever dispatched is conducted at this astonishing delay, across a gulf of space that is, even by the standards of the inner solar system, genuinely extraordinary. And yet, by the standards of the space between the stars, 24 billion kilometers is barely a beginning. The nearest star to our Sun, Proxima Centauri, lies at a distance of roughly 4.24 light-years from Earth. At Voyager 1's current speed of approximately 17 kilometers per second, which is the speed it is traveling right now relative to the Sun, it would take the spacecraft roughly 73,000 years to reach Proxima Centauri. Not 73 years, not 730 years, 73,000 years. A span of time longer than the entirety of recorded human history multiplied by more than 10. A span of time that carries us back past the last ice age, past the earliest cave paintings, past the origins of language, past every civilization that has ever left a single artifact or a single word. And Voyager 1 is not even headed in the direction of Proxima Centauri. Its trajectory is taking it toward the constellation Ophiuchus, in the general direction of the center of the galaxy, and the nearest star in roughly its path is a red dwarf called Gliese 445, located about 17.6 light-years away, which the spacecraft will approach to within 1.7 light-years in approximately 40,000 years. Not approach in the sense of fly past, since its trajectory does not bring it truly close to that star. Approach in the sense of reach the point of minimum distance before the trajectories diverge again. In 40,000 years. 40,000 years from now, when all of human civilization as we know it has long since transformed into something unrecognizable, when every building standing today has crumbled, when every ocean coast has shifted with the movement of ice and sea level, when languages have evolved into forms we could not recognize, a small spacecraft carrying a golden record and the memory of a single, brief, luminous moment of human curiosity will pass within 1.7 light-years of a dim red star that no human being on Earth can currently identify with the naked eye. The scale of this is not comfortable to hold, but holding it is part of what tonight's exploration is for. Let's think now about what Voyager 1 is actually experiencing right now as it moves through interstellar space, because the environment it is traveling through is not the nothing that the word emptiness might suggest, and understanding it adds texture to the journey. The interstellar medium, the substance of the galaxy beyond the heliosphere, is genuinely sparse. In the region of interstellar space that Voyager 1 is currently traversing, there are roughly a few particles per cubic centimeter, mostly protons and electrons, but also helium and trace amounts of heavier elements, along with dust grains and photons from distant stars. Compare this to the density of air you are breathing right now, which contains roughly 30 billion molecules per cubic centimeter, and the thinness of the interstellar medium becomes almost impossibly abstract. It is emptier than any vacuum achievable in any laboratory on Earth. It is, by any ordinary standard, nothing. And yet, it is not nothing. It has structure. It carries magnetic fields, remnants of the ancient processes that shaped the interstellar gas, and of the energetic events, supernova, stellar winds, the stirring effects of the galaxy's overall dynamics that have structured it over billions of years. The magnetic field that Voyager 1 is traveling through in interstellar space is oriented differently from the magnetic field of the solar wind, and one of the discoveries made possible by Voyager's crossing of the heliopause was a precise measurement of this orientation in the specific region of interstellar space that the spacecraft is traversing. This is data that no other instrument has ever collected, because no other instrument has ever been there. The cosmic ray environment beyond the heliopause is also different from what Voyager 1 experienced within it. Inside the heliosphere, the solar wind and the sun's magnetic field partially shield the inner solar system from the most energetic particles produced elsewhere in the galaxy. Galactic cosmic rays that have been accelerated to extraordinary speeds by supernova remnants and other violent events across the Milky Way. Outside the heliopause, Voyager 1 finds itself in a higher flux of these particles, as the shielding effect of the heliosphere is no longer present. The spacecraft's instruments measure the intensity of these cosmic rays, providing data about the radiation environment in the local interstellar medium that simply was not available before Voyager 1 arrived there. The spacecraft is also experiencing the photons of the cosmic microwave background, the ancient glow of the Big Bang that we explored in some detail in previous episodes on this channel, filling every corner of the universe with its faint 2.7 Kelvin warmth. And it is experiencing the collective light of every star and galaxy in the universe, arriving from all directions in an extraordinarily faint but real background of electromagnetic radiation. Voyager 1 is not in true emptiness. It is in a very thin, very ancient, very richly structured medium, and it is measuring that medium with instruments that are, by a remarkable conjunction of engineering and luck, still functioning nearly 5 decades after they were assembled. The power source that keeps Voyager 1 alive deserves its own careful exploration, because it is one of the more extraordinary engineering stories in the entire history of the mission, and because understanding it reveals both the ingenuity that went into the spacecraft's design and the specific ticking countdown that will eventually bring the mission to its end. Voyager 1 cannot use solar power. This was understood from the beginning of the mission's planning. The spacecraft would travel so far from the Sun that the intensity of sunlight at its position would be far too low to provide useful electrical power through solar panels, even if the mass and engineering constraints of a 1970s spacecraft had made large solar panels feasible, which they did not. Instead, the mission's designers chose a different approach, a radioisotope thermoelectric generator, or RTG. An RTG is a device that converts the heat generated by the radioactive decay of a specific isotope, in Voyager's case, plutonium-238, into electricity through the thermoelectric effect, exploiting the voltage that develops when two different conductors are held at different temperatures. It has no moving parts, no combustion, no complex chemistry. It simply relies on the continuous, predictable, inexorable decay of radioactive material, which produces heat over very long timescales and converts a fraction of that heat into the electricity that powers the spacecraft. The elegance of the RTG for deep space missions lies in its longevity and its reliability. The half-life of plutonium-238, the period over which the material's radioactivity decreases by half, is 87.7 years. This means that even decades after launch, the RTG continues to produce substantial heat and therefore substantial electricity. The power available to Voyager 1 decreases gradually over time, roughly 4 watts per year, but the decrease is slow enough that the spacecraft was still producing over 300 watts of electrical power decades into its mission, compared to the approximately 470 watts available at launch. The consequence of this gradual power decline is that the Voyager team has faced, over the decades, a continuous challenge of managing a shrinking power budget while maintaining the greatest possible scientific capability. Heaters that keep sensitive components from freezing in the extreme cold of deep space must be balanced against instruments that consume power. Systems that are no longer essential have been deactivated. The remaining active instruments have been preserved with extraordinary care because the team knows that every system shutdown is permanent. As the power continues to decline, the team has had to make increasingly difficult decisions about which instruments to turn off in order to preserve the remaining science capability. At some point, probably sometime in the late 2020s, the power available will become insufficient to keep any of the science instruments operating, and the mission will transition to a state where even the basic engineering data from the spacecraft's health systems becomes marginal. Eventually, in the 2030s at the latest by most estimates, even the transmitter that carries Voyager 1's signal across 22+ light hours of space will be unable to function, and contact with the spacecraft will be lost permanently. After that point, no new data will ever arrive. The spacecraft will continue on its trajectory, drifting outward into the galaxy at its current speed. But the thin thread of radio communication that has connected it to its makers since 1977 will have been severed, and it will move in complete silence, unknown and unknowing, through the interstellar dark. Let's spend some time now with the specific physics of why Voyager 1 will drift essentially forever, because the permanence of its journey is not merely a matter of no one having sent a retrieval mission. It is a consequence of the fundamental physics of motion in a universe where, in the vast spaces between the stars, there is almost nothing capable of stopping anything. Newton's first law of motion states that an object in motion remains in motion unless acted upon by an external force. This is one of those scientific principles that sounds abstract until you think carefully about the context in which it applies. And the context of interstellar space is one where it applies in the most stark and most literal way possible. On Earth, nothing moves forever. A ball rolled across a floor slows and stops because of friction with the floor and air resistance from the atmosphere. A car coasting to a stop does so because of friction in its drivetrain and between its tires and the road, and because of the resistance of the air it is moving through. Even a spacecraft in low Earth orbit gradually loses speed due to the extremely thin upper atmosphere that extends to orbital altitudes, and without occasional boosts from its engines would spiral inward and eventually re-enter the denser atmosphere below. In interstellar space, none of these stopping mechanisms applies. The interstellar medium is so thin that its resistance to a moving object is essentially zero for any practical purpose. The gravitational influence of the Sun, while it extends technically to enormous distances, falls off with the square of the distance, meaning that at the distances Voyager 1 has already reached, the Sun's gravitational pull is so faint as to have only the most minuscule effect on the spacecraft's speed. The gravitational fields of the nearest other stars are even more distant and therefore even more negligible. The only significant gravitational influence that Voyager 1 will encounter on any timescale shorter than the age of the galaxy would be a close encounter with another star, which, given the extraordinary distances between stars and the specific trajectory Voyager is following, simply will not happen. The result of this near-perfect absence of forces is that Voyager 1's motion, minus the almost imperceptibly tiny effects of the residual gravity of the Sun and stars, will continue essentially unchanged, essentially forever. It will drift at roughly its current speed, in roughly its current direction, without slowing, without stopping, without turning, long after the last evidence of its origin has been erased from the universe. The numbers here acquire a quality that is almost vertiginous. In 1 billion years, Voyager 1 will have traveled approximately 500,000 light-years from where it is today. In 10 billion years, which is roughly the remaining lifespan of the Sun as a stable star, it will have traveled 5 million light-years, farther than the distance from the Milky Way to many neighboring galaxies. In 1 trillion years, it will be so far from the original solar system that the region of space it departed from will be essentially unrecognizable, reshaped by billions of years of stellar evolution, galactic dynamics, and the slow, grand transformations of cosmic structure. And through all of this, the spacecraft itself will persist. Absent some extraordinary collision with a large enough body, the physical structure of Voyager 1 will remain intact for timescales that are genuinely incomprehensible. The gold record attached to its body, the copper disk with its gold plating containing sounds and images of Earth, may survive for billions of years in the absence of any significant erosive force. The aluminum frame, the electronic components sealed within it, the magnetometers and the plasma wave instruments and the faded paint and the golden record and the bolt that holds it all together will drift through the dark, essentially unchanged, for longer than the current age of the universe. The golden record is one of the most extraordinary artifacts that human beings have ever created, and it deserves its own careful and unhurried exploration because it sits at the heart of what Voyager 1 ultimately represents, philosophically and emotionally, and in terms of what we are communicating about our species to whoever or whatever might eventually encounter it. The Golden Record was conceived and produced under the direction of Carl Sagan, then a professor at Cornell University who chaired the committee assembled by NASA to decide what should be placed on it. The premise of the record was that the Voyager spacecraft, once they left the solar system, would drift through interstellar space for timescales so vast that the possibility of detection by another civilization somewhere in the galaxy, however remote, was worth taking seriously. If any other technological civilization in the Milky Way ever found and examined the spacecraft, what should they find on it? The record is a 12-inch gold-plated copper disc, a format chosen because the committee believed that any sufficiently advanced civilization capable of traveling to or detecting the spacecraft would be capable of working out how to play it, with a set of instructions for playback etched on its cover, along with a pulsar map that encodes the position of the solar system relative to 14 pulsars, rotating neutron stars with distinctive and stable pulse rates that serve as unique markers in the galaxy. The pulsar map was designed by Sagan's colleague Frank Drake, who also designed the famous Drake equation for estimating the number of communicating civilizations in the galaxy. The content of the record was assembled over a period of roughly 6 months, an extraordinary effort given the time pressure involved with the launch schedule. It includes 116 images in analog encoding, covering topics from mathematics and physics to Earth's geography, biology, human anatomy, and human civilization. It includes sounds of Earth, among them wind and rain and thunder, the sounds of surf and birds and an elephant and the singing of whales, a crying baby and a mother's first words to it, laughter and a kiss. It includes a spoken greeting in 55 human languages, from Sumerian and ancient Akkadian through dozens of modern languages, and a greeting from the Secretary General of the United Nations of the era, and from an 8-year-old child named Nick Sagan, who is the son of Carl Sagan. The music selection was perhaps the most debated. The committee ultimately included 90 minutes of music from human cultures around the world, including Bach, Beethoven, Mozart, Louis Armstrong, Blind Willie Johnson, Chuck Berry's Johnny B. Good, Azerbaijani folk music, Navajo night chants, Peruvian panpipes, Japanese shakuhachi, Georgian chorus, and many others. The range was deliberately vast, an attempt to represent the diversity of human musical expression rather than prioritizing any single tradition. It is the most sophisticated message that our species has ever sent into the cosmos, and it is attached to a small spacecraft currently drifting through interstellar space at 17 kilometers per second. Carl Sagan described the golden record as humanity's message in a bottle, cast into the cosmic ocean. The metaphor is more accurate than it might initially seem. A bottle cast into the ocean drifts on currents, following paths determined by wind and water rather than any human intention, and its eventual fate, whether it is found or not, by whom, in what condition, after how long, is entirely beyond the control of the person who sent it. The golden record is in this sense a genuine act of cosmic faith, a decision that the act of reaching out, of saying we were here, we made this, we are curious and musical and varied and alive, is worth doing even with no expectation of response. Let's think carefully about the person who made that record possible, because Carl Sagan's presence in this story is not incidental. He is, in a very specific and very important way, the reason the Voyager spacecraft carries anything more than instruments and engineering hardware. Sagan was, among many other things, a deeply committed advocate for the idea that humanity's exploration of space should carry within it an awareness of our cosmic context, an acknowledgement of our smallness, and a spirit of genuine outreach toward whatever else might exist in the universe. He had argued, since at least the early 1970s, that if we were sending spacecraft into interstellar space, we should put something on them that communicated who we were. He had made this argument successfully once before. Pioneer 10 and Pioneer 11, earlier spacecraft that also traveled through the outer solar system and into interstellar trajectories, each carried a small metal plaque designed by Sagan and Drake and his then collaborator Linda Salzman Sagan, showing a man and a woman, a diagram of the spacecraft's origin, a representation of our solar system, and a pulsar map. These plaques were the first human artifacts sent into interstellar space that intentionally communicated something about their creators. For Voyager, Sagan wanted more. He wanted music. He wanted sounds. He wanted the diversity and the richness and the specificity of human experience to be represented, not just a diagram of anatomy and orbital mechanics. He recruited a team that included the writer and producer Timothy Ferris, the artist Anne Druyan, who would later become his wife, and many others, and they worked through months of extraordinary creative and intellectual effort to assemble what is now the Golden Record. There is a story about the making of the Golden Record that is, for many people who hear it, one of the more quietly moving things in the entire Voyager story. Anne Druyan, in the process of researching the content of the record, meditated specifically on what it means to be in love, on the biological, cultural, neurological, emotional reality of falling in love, as she was preparing to have her brainwaves recorded and included on the record. She was at that time developing feelings for Carl Sagan that would eventually become their marriage, a marriage that lasted until his death in 1996. Those feelings, meditated on specifically and intentionally, are encoded in the brainwave data on the golden record. The emotional reality of a specific human being falling in love is aboard a spacecraft currently drifting through interstellar space, and it has been for more than 4 decades. Sagan later wrote that if, somewhere in the depths of the galaxy, the Voyager spacecraft is found by some civilization curious about who built it, and if that civilization somehow manages to decode the brainwave data and understand it, they will receive a transmission from Anne Druyan as she was in 1977, thinking about love. The thought is simultaneously scientifically improbable and emotionally extraordinary, and it says something important about the spirit in which the record was made. It was not made purely as a scientific document. It was made with genuine human feeling, with the same impulse that has led human beings throughout history to write things in places they thought might outlast them, to carve names in stone and plant seeds in ground they knew they would not see to harvest. Let's turn now to the reality of operating Voyager 1 in its present state, because the daily, ongoing work of maintaining contact with the most distant human object in existence is itself an extraordinary story, one that involves a small team of engineers and scientists who have, in some cases, dedicated their entire professional lives to a mission that launched before many of them were born. The communications link between Voyager 1 and Earth relies on NASA's Deep Space Network, a system of large radio antenna complexes located in California, Spain, and Australia, positioned around the Earth so that as the planet rotates, at least one complex always has a line of sight to any spacecraft in deep space. The Deep Space Network receives and transmits signals to dozens of active spacecraft simultaneously, managing the communication needs of missions scattered across the solar system and beyond. The signal from Voyager 1, when it arrives at a Deep Space Network antenna, has traveled for more than 22 hours at the speed of light and has weakened enormously over that journey. The received power of Voyager 1's signal is approximately 20 billion times smaller than the power required to run a digital watch. The antennas that receive it must be extraordinarily sensitive, and the digital signal processing required to extract useful data from the noise requires sophisticated technology that itself has been upgraded multiple times over the decades, even as the spacecraft transmitting the signal has remained essentially unchanged since its construction in the 1970s. The engineering team responsible for the spacecraft is one of the most specialized groups of people in the world. They must understand in detail a system designed and built 50 years ago, using design philosophies and computing architectures that have largely disappeared from modern engineering practice. The documentation and institutional knowledge that would allow the team to work effectively with the spacecraft has required enormous care to maintain and transmit to successive generations of engineers, since the original designers have long since retired or passed away. There have been moments in recent years when this challenge became acutely visible. In 2022, the spacecraft began returning garbled data, sending back nonsense codes that did not correspond to any recognizable command or status report. The team eventually traced the problem to a single memory chip in the flight data system that had been corrupted, likely by radiation damage accumulated over decades in space. The solution: developing and uploading a software patch to a 45-year-old computer located 23 billion kilometers away across a communication round trip that took 45 hours, was a remarkable piece of engineering problem-solving conducted under conditions of extraordinary constraint. The team fixed it. The spacecraft resumed normal data transmission. The quiet, methodical competence of the people who tend to Voyager 1 from an office building in Pasadena, California, navigating a problem no engineering school had specifically trained them to solve, is part of the ongoing human story that the mission represents. The science that Voyager 1 has produced in interstellar space is not merely historical curiosity. It is active, current, frontier science that no other instrument is capable of producing, and understanding it helps explain why the engineering team works so hard to keep the spacecraft operational for as long as possible. The region of interstellar space that Voyager 1 is currently traversing is called the local interstellar cloud, a region of slightly warmer, slightly denser interstellar medium that is thought to be a remnant of ancient supernova activity in this part of the galaxy, extending perhaps 30 light-years across. The conditions within the local interstellar cloud are slightly different from the average conditions in the broader interstellar medium, and Voyager 1's instruments are providing the first direct measurements of these conditions from the inside. The plasma wave system on Voyager 1, one of the instruments that has survived and continues to function, detects oscillations in the electron density of the surrounding medium. These oscillations produce signals at very specific frequencies that correspond to the plasma frequency, a characteristic of the medium that depends on how many free electrons are present per unit volume. By measuring these frequencies, the team can determine the density of the interstellar plasma that Voyager is currently moving through with a precision that was not previously available. The spacecraft has detected on several occasions since entering interstellar space what are called electron density increases, compressions of the local plasma produced by the arrival of powerful coronal mass ejections from the Sun, whose effects propagate outward through the heliosphere and beyond, compressing and perturbing the interstellar medium even at the enormous distances Voyager 1 has reached. These measurements are providing the first direct glimpse of how the Sun's most energetic outbursts interact with the interstellar medium. Data that models of heliospheric physics had predicted, but that could only be confirmed from a position in interstellar space. The cosmic ray measurements made by Voyager 1's functioning instruments continue to map the energy spectrum and composition of galactic cosmic rays in a specific location that is changing as the spacecraft moves deeper into the interstellar medium. Every year, Voyager 1 is in a slightly different location than the year before, and the cosmic ray data from each year adds to a unique, irreplaceable record of conditions in this specific region of the galaxy. The magnetic field measurements, while the primary magnetometer has become more challenging to use as power constraints have increased, have provided data about the orientation and intensity of the local interstellar magnetic field that is directly relevant to understanding how the heliosphere interacts with the medium through which it moves, and how our star fits into the larger structure of the galaxy's magnetic environment. None of this science can be obtained from Earth-based observatories, from spacecraft in the inner solar system, or from any other instrument currently in existence. Voyager 1 is the sole source of this data, and when the spacecraft's transmitter finally falls silent, this specific window of observation will close permanently. There will be no replacement, no second chance. The data being gathered right now in the coming years before the transmitter fails is unique and non-renewable. Let's spend time now on the experience of receiving the signal from Voyager 1 and what it must feel like to be part of the team that does this work every day. Because there is something in that daily experience that touches on something larger about the relationship between human beings and the extraordinary things they sometimes manage to build. Imagine sitting in a control room, looking at a display that shows a signal arriving from beyond the edge of the solar system. The signal left the spacecraft more than 22 hours ago. What you are receiving now is a message from the past, from a machine in a place no human being has ever been, reporting on conditions in a place that no human eye has ever seen and that no human spacecraft has reached except this one. The signal is extraordinarily faint, drowned by noise at a level that requires sophisticated signal processing to extract any useful content at all. But when it is extracted, when the data is decoded and the engineering telemetry is read out and the scientific measurements are displayed, what you have is genuine knowledge, real information about real conditions in a real location in interstellar space, obtained through an instrument that has been traveling continuously since 1977 and has never once stopped sending data as long as it had power to do so. The engineers and scientists who have worked on Voyager 1 over the years describe a relationship with the spacecraft that goes beyond purely professional engagement. People who have spent decades working with Voyager speak about the mission with an affection and a protectiveness that borders on the personal. The spacecraft is, in a very real sense, a member of the team that has been in continuous operation for longer than most current members of the team have been alive. There is a specific kind of poignancy in the knowledge that every year the signal gets slightly weaker, the power budget gets slightly tighter, and the range of instruments that can be kept running narrows slightly further. The people who work with Voyager 1 know that they are in the final chapter of direct contact with the most distant human-made object in existence. They know that when the transmitter finally goes silent, no one will ever hear from it again. And they know that the spacecraft will continue on its journey regardless, drifting into the dark without any ability to tell them where it is or what it is experiencing. There is something in this knowledge, this combination of extraordinary achievement and approaching loss, that has a quality similar to other experiences of finite beauty in human life. The final days of something irreplaceable, approached with both grief and gratitude, tended to with extraordinary care because the care cannot be extended indefinitely. Let's think now about the meaning of Voyager 1's eternal journey in a broader cosmic context, because placing it against the backdrop of what we now know about the scale of the universe and the timeline of cosmic history adds dimensions to the story that are genuinely worth sitting with. Voyager 1 was launched from a planet orbiting a star that is roughly 4.6 billion years old, in a galaxy that is roughly 13.5 billion years old, in a universe that is roughly 13.8 billion years old. These numbers establish that our Sun and our planet are relatively young by cosmic standards, and that the universe has been producing stars and planets and potentially life for a span of time that dwarfs the entire history of our solar system. The lifetime of the Sun as a stable, hydrogen-fusing main sequence star is estimated at roughly 10 billion years total. We are roughly halfway through this lifetime now. In approximately 5 billion years, the Sun will have exhausted the hydrogen in its core and will begin to expand, first into a subgiant, then into a red giant, eventually swelling outward to perhaps 50 or 100 times its current diameter. The inner planets, Mercury and Venus, will likely be consumed. Earth may or may not be, depending on the exact trajectory of the Sun's expansion and on the degree to which orbital mechanics push Earth's orbit outward as the Sun loses mass. Either way, the Earth as we know it will not survive the Sun's red giant phase in any form that could harbor human life or any descendant civilization. The surface will be sterilized, the oceans boiled away, the atmosphere stripped or chemically transformed. The planet will become lifeless if it was not already made lifeless by the changes leading up to that phase. In 5 billion years, Voyager 1 will be roughly 2.5 million light-years from where it is today. It will have long since lost any power. It will be drifting in complete silence, an inert object in the intergalactic medium, because by that time its trajectory may have carried it out of the Milky Way entirely, depending on the gravitational interactions it has experienced over the intervening billions of years. It will be utterly unrecognizable to any intelligence that might have descended from the civilization that built it, assuming any such intelligence exists, because that civilization will have had to have adapted to an entirely different situation in the wake of the Sun's evolution. The Sun that Voyager 1 left will have become, by this point, a white dwarf, a small, hot, dense ember cooling slowly over trillions of years. Voyager 1, somewhere in the vastness between the galaxies or drifting through some far region of the Milky Way's halo, will outlast the star that powered the civilization that built it. This thought has a specific quality that is hard to name precisely. It is not quite sad and not quite triumphant and not quite peaceful, though it contains elements of all three. The machine outlives the maker. The message outlives the sender. The bottle drifts long past the dissolution of the civilization that cast it into the sea. There is a specific moment in the Voyager 1 story that Carl Sagan made famous, and that has become, for many people, one of the most emotionally resonant photographs ever taken. That moment occurred in February 1990, when Voyager 1 was at a distance of approximately 6 billion kilometers from Earth, well beyond the orbit of Neptune, and was commanded to turn its cameras back toward the Sun and take a series of images of the solar system as a whole. The result was a mosaic photograph of the planets, most of them barely visible against the darkness of space. Earth appears in one of these images as a tiny point of light, less than a pixel in diameter, caught in a scattered ray of sunlight from the Sun's brightness overwhelming the camera. This image was named the pale blue dot by Carl Sagan, who wrote about it in terms that have been quoted so often since their publication that the words themselves have become one of the more widely recognized pieces of scientific writing of the 20th century. We will not reproduce those words here, because reproducing exact copyrighted text is something we do not do. But the essence of what Sagan expressed was this: looking at the photograph, at the barely visible point of light that represents our planet and everything that has ever lived on it, and everything we have ever considered important, places all of human history and human striving in a context that is simultaneously humbling and moving. Every person who has ever lived, every kingdom and every civilization, every moment of beauty and every act of cruelty occurred on that point of light. And the universe, vast and ancient and indifferent, contains billions of such points, most of them unknown to us, all of them with their own histories and their own inhabitants. The image was taken as Voyager 1's cameras were about to be shut down permanently, since there was nothing more of scientific interest for them to photograph in the outer solar system, and since the power needed to operate them was needed for other systems. The pale blue dot images were, in a sense, a final act of looking back before the spacecraft committed to its permanent forward journey. What the image showed, and what the act of taking it expressed, was not a declaration of human insignificance. Sagan was not arguing that we were small and therefore unimportant. He was arguing something more subtle and more important, that the smallness of our place in the cosmos was a reason for a specific kind of care and a specific kind of compassion toward each other and toward the world we share, precisely because the world we share is all we have, and it is genuinely, magnificently rare in the dark. Let's think now about the other spacecraft that have followed Voyager 1 and Voyager 2 in terms of their trajectories, and about whether any future mission might eventually reach the interstellar medium in the same sense, because understanding the broader context of deep space exploration helps frame what makes Voyager 1 specifically unique. Voyager 2, which took a different trajectory through the outer solar system, crossed the heliopause in November 2018, making it the second human-made object to enter interstellar space. It is currently traveling at approximately 15 kilometers per second relative to the Sun, somewhat slower than Voyager 1 and in a different direction. The two spacecraft are providing simultaneous measurements of interstellar space conditions in two different locations, which is scientifically valuable for understanding how uniform or varied the local interstellar medium is, at the scale of the separation between the two probes. Pioneer 10 and Pioneer 11, launched in the early 1970s, and the earlier Outer Solar System missions are also on trajectories that carry them into interstellar space, but contact with both Pioneer spacecraft was lost years ago, Pioneer 10 in 2003 and Pioneer 11 in 1995. So they are traveling silently without returning any data. No mission currently operating or planned for the near term will reach interstellar space within the operational lifetimes of anyone currently working in the field. The Voyager spacecraft achieved their extraordinary range through the fortuitous combination of the gravitational assistance from the outer planets, which amplified their speed dramatically, and the 4 to 5 decades of continuous travel since. A mission to the heliopause that started from rest would require either a far more powerful propulsion system than anything currently in operation, or a much longer travel time than Voyager required. There have been proposals for a dedicated interstellar probe mission, a next-generation spacecraft specifically designed to study the heliosphere and local interstellar medium from the outside. Various architectures for such a mission have been studied, with some proposals calling for a spacecraft significantly faster than Voyager, achieved through a combination of a large conventional rocket and a close solar flyby to pick up speed from the Sun's gravity. Such a mission could potentially reach the heliopause in as few as 15 years, far sooner than the 35 years it took Voyager 1. But as of the mid-2020s, no such mission had been formally approved or funded, meaning that Voyager 1 and Voyager 2 remain the only eyes and ears of humanity in interstellar space for the time being. The uniqueness of the Voyager mission in this context, its combination of extraordinary distance, continued operation, and scientific productivity, is something that will not be replicated for years or decades to come, and possibly not in the same form at all. There is a particular and genuinely interesting scientific debate that the Voyager crossings of the heliopause have contributed to, and it concerns a question that was not fully answered before Voyager arrived at the heliopause. What exactly does the boundary of the heliosphere look like, and how does our Sun compare to other stars in terms of the structure of its stellar wind bubble? Before Voyager reached the heliopause, models of the heliosphere's structure predicted the existence of a specific sequence of boundaries. First, a termination shock, where the solar wind slows from supersonic to subsonic as it is compressed by the surrounding interstellar medium. Second, a heliosheath, the turbulent region between the termination shock and the heliopause, where the shocked solar wind material piles up. And third, the heliopause itself, the actual boundary between solar wind material and interstellar material. Voyager 1 crossed the termination shock in December 2004, at a distance of about 94 astronomical units from the Sun. This was somewhat closer than some models had predicted, suggesting that the heliosphere is slightly smaller in the direction Voyager 1 was traveling than some theoretical estimates had suggested. The heliosheath, the turbulent region between the termination shock and the heliopause, turned out to be thicker and more complex than expected, full of a back-and-forth interchange of particles that was not fully anticipated. The heliopause itself, crossed in August 2012, was also somewhat different from what had been expected. In particular, the magnetic field orientation at the heliopause and just beyond it was not what most models had predicted. The direction of the interstellar magnetic field, when it was finally measurable from inside the interstellar medium, differed from the direction inferred from models based on observations of interstellar material from inside the heliosphere. This discrepancy has been the subject of ongoing scientific discussion and continues to inform the development of improved models of how our heliosphere interacts with the local interstellar medium. One implication of these findings is that our understanding of the Sun as a stellar system, as a bubble in the interstellar medium, is less complete than we thought before Voyager crossed the boundary. The specific geometry of the heliosphere, the exact shape and size of its boundary regions, the direction and intensity of the local interstellar magnetic field. All of these are more complex and more variable than some of the cleaner models that were standard before Voyager provided direct measurements. This is not a failure of science, but a success of it. The models were wrong in specific ways, and knowing exactly how they were wrong is precisely what drives the development of better models. Let's spend some time now with the question of what happens to Voyager 1 over timescales that are genuinely difficult to think about. Timescales measured not in decades or centuries, but in millions and billions and trillions of years. Because the physics of the spacecraft's eternal drift produces a timeline that is as strange and as moving as any in the history of the universe. In about 40,000 years, as we established earlier, Voyager 1 will reach the point of closest approach to Gliese 445, the red dwarf star that happens to lie roughly in its current direction of travel. The closest approach will be about 1.7 light-years, which is close enough to be noteworthy on a galactic scale, but not close enough for any significant gravitational interaction. The spacecraft will not be captured by the star's gravity. It will not be heated significantly by the star's radiation. It will simply drift past, in the outer darkness well beyond any planetary system that might orbit the star, and continue outward. Over the course of millions of years, the spacecraft's trajectory will be very slowly and very subtly modified by the combined gravitational effects of the stars it passes near and the overall mass distribution of the galaxy. The Milky Way is not a static structure, but a dynamic one, with billions of stars moving in complex orbits around the galactic center, and a spacecraft drifting through this environment will experience, over long timescales, a series of tiny gravitational nudges that gradually alter its path. This process, called gravitational stirring or perturbation by stellar encounters, is extremely slow but relentless, and over hundreds of millions to billions of years, it will fundamentally alter the spacecraft's trajectory from its current direction. In several billion years, assuming Voyager 1 has not encountered any large body, which is extremely unlikely given the emptiness of the spaces between stars, the spacecraft will have drifted somewhere into the outer halo of the Milky Way, or potentially beyond the galaxy entirely into the local group, depending on the specific trajectory alterations it has experienced. At this point, it will have been silent for billions of years, its transmitter long since failed, its power source long since exhausted, its instruments inert. It will be a cold, dark, drifting artifact, carrying the golden record and the memory of its origin in a universe that has changed almost beyond recognition. In tens of billions of years, the Milky Way will have merged with Andromeda, as we explored in our episode about the local group, and the resulting merged galaxy, Milkomeda, will be a different structure than either of its progenitors, an elliptical rather than a spiral, reshuffled by the violence and the slow gravitational mixing of the collision. Voyager 1 will be somewhere in this merged structure, or in the surrounding halo, or in the intergalactic space nearby, drifting still. In trillions of years, the stars within the merged galaxy will have mostly burned out, leaving behind a collection of cooling stellar remnants. White dwarfs, neutron stars, and black holes will orbit in the increasingly cold and quiet darkness. Voyager 1, still drifting at roughly its current speed, though gradually perturbed by whatever gravitational interactions it has experienced, will be somewhere in this quiet stellar graveyard. And still, in all probability, the physical structure of the spacecraft will be essentially intact. The gold plating on the record will still be gold. The copper beneath it will still be copper. The atoms of aluminum and titanium and platinum and gold that were mined from the Earth in the 1970s and shaped into this machine will still be those atoms, unchanged in their fundamental nature by any process that is likely to affect them in interstellar space. the universe in which they exist will have changed almost entirely. But the atoms themselves and the structure they form will remain. There is one more aspect of the Voyager story that deserves careful, extended attention, and it concerns the people who conceived and built and launched and operated the mission and what their work represents in the context of human history. The Voyager program was the product of a specific confluence of factors: the existence of the Grand Tour opportunity, the institutional commitment of NASA and the Jet Propulsion Laboratory, the Cold War competition that had generated the funding and the organizational will for ambitious space exploration, and, critically, the specific cluster of extraordinary people who happened to be in the right place at the right time, with the right skills and the right vision. Edward Stone, who served as the Voyager project scientist for many decades and who delivered many of the landmark announcements about the mission's findings, including the 2013 announcement that Voyager 1 had entered interstellar space, is one of the central figures in this story, a person whose career commitment to a single mission spanning more than 4 decades is itself extraordinary. John Cassani, the original project manager, Bruce Murray, who directed JPL during the planetary encounter period, and the hundreds of engineers and scientists who designed, built, tested, and operated the instruments are all part of a community of people who created something whose significance far outlasts any individual career or life. Carl Sagan's contribution, through the Golden Record and through the cultural communication work he did to explain the meaning of the mission to the broader public, is inseparable from what Voyager 1 ultimately represents. Without Sagan, the spacecraft would carry instruments and engineering, but nothing that speaks to what the mission means beyond the data it returns. The Golden Record transforms Voyager 1 from a scientific instrument into something more: an emissary, a message, a gesture. The decision to include the record was not universally supported within NASA. Some officials felt it was an unnecessary expense and an unscientific indulgence. Sagan and his colleagues argued that the record was precisely the kind of thing that made the difference between a mission that was important and a mission that was historic, between a scientific success and a cultural achievement. The record went on the spacecraft, and half a century later, in the common cultural understanding of what Voyager 1 represents, the Golden Record is as central to the story as any of the scientific instruments. The people who made Voyager 1 represent something important about human civilization in the late 20th century, a moment when the combination of political will, technological capability, scientific knowledge, and cultural ambition made possible something that had never been done before, and that will not be possible in exactly the same form again. The Grand Tour opportunity does not recur for another century and a half. The specific institutional and political context of the 1970s space program is gone. The specific people who came together to make this mission are either aged or departed. What remains is the mission itself, still operating after nearly 5 decades, and the spacecraft it sent into the dark. Let's think carefully now about what the permanent, eternal nature of Voyager 1's journey means in a deeper sense, not merely as a fact of physics, but as a statement about the relationship between human beings and the universe we inhabit. We explored in our episode about dark matter the idea that the universe is composed mostly of something we cannot directly perceive or understand. We explored in our episode about the local group the idea that the overwhelming majority of the universe is permanently beyond our reach. We explored in our episode about the universe's dead zones the idea that most of the cosmos is, by various measures, inhospitable to the conditions that allow life and intelligence to develop. Taken together, these facts sketch a picture of a universe that is vast, ancient, mostly dark, and largely indifferent to our existence. And yet, into this vast, ancient, mostly dark, largely indifferent universe, we have launched something. not as a test or a military asset or a commercial venture, but as a genuine, deliberate attempt at communication, at expression, at the cosmic equivalent of leaving a note that says, "We were here." This act is small by cosmic standards. The spacecraft is tiny. The power of its transmitter is negligible. The golden record, even if found in 1 billion years by some civilization with the capability to decode it, is one message in a universe that contains whatever else it contains, and the probability of any specific message being found in any specific period of time in a galaxy of 400 billion stars is not high. And yet, the act is not nothing. The act is not without meaning, not without importance, not without a specific and irreducible dignity that comes from the human capacity to reach beyond the immediate and the practical and the self-interested towards something larger. The golden record is a love letter written without knowing if there is anyone to receive it, kept alive by the same impulse that has led human beings throughout history to create art and music and stories, to communicate with the future and with the unknown, to extend the reach of consciousness into territories that will not see it returned. When we think about Voyager, one drifting forever in the dark, we can think of it as something lost, something receding beyond all contact, carrying a message that will almost certainly never be read. And this is true. Or we can think of it as something sent, deliberately and with care and with genuine human feeling, into a universe that may or may not contain anyone to receive it, but that is, at any rate, the universe we live in, and the only one we have to cast our messages into. The drift is eternal. The message is real. The act of sending it was human in the deepest sense of that word, the reaching towards something that will almost certainly not answer, because the reaching itself is what we are. Let's think about a specific question that rarely comes up in discussions of Voyager 1, but that is genuinely interesting and genuinely important. What would it mean for another civilization to find the spacecraft? The scenario requires a number of conditions to be met simultaneously. There must be, somewhere in the Milky Way or beyond, a technological civilization capable of either traveling to the spacecraft or detecting it through some means, perhaps through the residual heat signature of its cooling metal, or through some electromagnetic signature we cannot currently predict would be detectable. That civilization must be curious enough about artificial objects to investigate rather than ignore. And the timing must work out such that the civilization exists when the spacecraft can be found, which, given the timescales involved, means at some point in the next several billion years before the spacecraft has been so perturbed in its trajectory by stellar encounters as to become effectively untraceable to its origin. If all of these conditions were met, what would the finders learn? From the spacecraft's structure, they could learn that it was made by beings who had mastered metallurgy, electronics, nuclear physics sufficient to build an RTG, and the gravitational mechanics required to navigate through a planetary system using gravitational assists. From the golden record and its instructions, they could learn about our mathematics, our physics, our biology, our geography, our music, our languages, and our emotional lives. From the pulsar map, they could determine roughly when the spacecraft was launched and where in the galaxy it came from. This is a remarkable packet of information about a civilization, far more than the bare physical structure of the spacecraft could convey alone. But it is also, necessarily, a time capsule, a picture of a civilization as it was in 1977, not as it might be at the time of discovery. Whatever civilization finds Voyager 1, if any does, will be finding a historical document rather than a live communication, an artifact from a past they knew nothing about, a message from a civilization that may or may not still exist in any recognizable form. The strangeness and the poignancy of this is part of what makes the Golden Record such a compelling object of reflection. It was made with full knowledge that it was being made in 1977 in the early stages of the space age by a civilization that could not possibly predict what the future would bring. The people who made it knew they were making a message in a bottle, not a real-time communication. They made it anyway, with as much care and as much thoughtfulness and as much genuine love as they could bring to the task, because the making of it was its own justification, regardless of what happened to the bottle. Let's spend a little time with the sensory experience of space as Voyager 1 would encounter it, if the spacecraft had senses. Because thinking about what the journey is actually like from the perspective of the object making it adds something to the overall picture. Voyager 1 is in deep darkness. The sun, which at Earth appears so large and so bright that looking directly at it can damage the eyes, is at Voyager 1's current distance a very bright but small point of light, roughly 150 times dimmer than it appears from Earth. It would still be by far the brightest point in the local sky, dominating the immediate field of view in a way that no other object could, but it would not provide the flooding, warming light that it does to Earth. The spacecraft's surfaces are extremely cold, not because of the darkness alone, but because of the combined effect of being very far from a heat source and being in a near-perfect vacuum that allows no conduction or convection, only radiation as a mechanism of heat exchange. The stars visible from Voyager 1's position would be the same stars visible from Earth, since even its extraordinary distance from Earth is negligible compared to the distances to the nearest stars. But they would be visible without the atmospheric blurring and scattering that affects Earth-based observations. The night sky, as seen from Voyager 1, if it had eyes to see it, would be the clearest possible view of the galaxy. Every star a steady, unwavering point of light, the Milky Way a river of starlight undistorted by any atmosphere. The other galaxies tiny but real smudges of ancient light scattered across the background. Voyager 1 is also in almost complete silence in the sense that there is no air to transmit sound waves. The plasma oscillations that its instruments detect are electromagnetic rather than acoustic. The impacts of the rare interstellar dust grains that strike it produce no sound. The spacecraft moves through the void in complete sensory quiet, sending its faint signal backward to the distant warmth of home and receiving nothing in return except the commands and queries that arrive, delayed by 22 hours, from the people in Pasadena who are still, for now, listening. There is something about this image, the tiny machine in its vast, silent, cold surrounding, sending its signal faithfully homeward from a place that no one can see or hear or touch, that has a quality that is hard to name precisely. It is not quite loneliness, because the machine does not experience loneliness. It is not quite heroism, because the machine does not experience heroism. It is something that the machine itself cannot experience, but that we can experience on its behalf. The quality that comes from the gap between the scale of the surrounding universe and the smallness of the human thing placed within it, still functioning, still sending, still reaching back toward the warmth it came from. We are drawing near the close of tonight's long exploration, and before we let it settle into the quiet of whatever evening or night surrounds you, let's gather the threads together and let them be what they are. Voyager 1 was built by human hands from materials mined from the Earth, assembled in a building in California, launched on a rocket whose fuel burned for minutes, and then spent decades threading its way through the gravitational architecture of the outer solar system before crossing, in 2012, into a region of space that no human artifact had ever entered. It carries instruments that continue to return data about the interstellar medium from a position that no other instrument can occupy. It carries a golden record that contains the music and voices and sounds and images of a civilization that existed in 1977, encoded with care and hope by people who understood they were reaching towards something they could not fully imagine. It will drift when its transmitter finally goes silent for billions of years through a universe that will continue changing around it while it changes not at all, carrying its cargo of human expression into a darkness so deep and so permanent that the word forever is not an exaggeration. And we can know all of this. We can sit with it tonight in the specific quiet of wherever we are and hold the whole of it. The extraordinary small beginning, the decades of faithful service, the crossing into the genuinely unknown, the approaching silence, the eternal drift, the golden record and its contents, and the act of sending it, which was perhaps the most human thing we have ever done in space. The universe is, as we have explored across many episodes on this channel, vast and ancient and mostly dark. It is composed largely of things we cannot see and governed by processes that dwarf any human intervention. It will continue long after every trace of us is gone, and it will not miss us when we are gone, because the universe does not miss anything. But we have sent something into it, something small and fragile and beautifully made, carrying sounds of whales and rain and music and laughter, moving through the dark at 17 kilometers per second without slowing, heading toward a future so distant and so changed that nothing we know will remain familiar in it. Moving there forever. There are nights when that thought is quietly overwhelming. And there are nights when it is quietly perfect, when the idea that something human is out there in the dark, still moving, still carrying what we put on it, still faithful to the trajectory that physics gave it all those decades ago, feels like enough. More than enough. Genuinely extraordinary. If tonight's slow journey alongside Voyager 1 has given you something worth carrying into rest, perhaps a new sense of what the word forever means when it is attached to a machine the size of a small car built by human beings in 1977, you are always welcome to return to Beyond the Cosmos whenever curiosity calls you back. There is always more to explore, and always, here, a quiet space to explore it together. For now, let the signal fade the way Voyager 1's signal will someday fade, gradually, over years, without drama, until the last bit of data arrives and there is nothing more to say. Let the machine drift. Let the dark hold it. Let your breathing slow, and let this extraordinary small fact settle into the background of your awareness, where it will continue to mean something every time it occurs to you again. Let's go back and spend considerably more time on the specific physics and engineering of how Voyager 1 achieved its extraordinary velocity, because the gravitational assist maneuvers that gave it the speed to eventually reach interstellar space are among the more elegant pieces of applied physics in the history of the space program, and understanding them properly deepens the appreciation of what the mission accomplished. A spacecraft launched from Earth with conventional rocket propulsion can reach a certain maximum speed, determined by the energy available from the fuel it carries. For the Voyager spacecraft in 1977, this initial speed was insufficient to reach the outer solar system on any reasonable timescale, and even if it had been sufficient, the spacecraft would have arrived at each outer planet one at a time without the additional velocity needed to continue onward efficiently to the next. The solution to this problem is a technique called the gravitational slingshot or gravitational assist, which exploits the way that a massive planet's gravity can be used to redirect and accelerate a spacecraft without any additional fuel expenditure. The physics of how this works is genuinely counterintuitive at first encounter, because it seems to violate the intuition that gravity can only pull things toward it, not speed them up and send them on their way. The key is that a spacecraft approaching a planet from behind, in the sense of approaching in the same direction the planet is moving around the Sun, and then swinging around the planet in the appropriate trajectory, effectively borrows velocity from the planet's own orbital motion. The spacecraft gains speed from the interaction, while the planet loses an infinitesimally small amount of speed from its own orbit. From the reference frame of the Sun, the spacecraft has gained kinetic energy equal to twice the planet's velocity, multiplied by the change in the spacecraft's velocity relative to the planet. From the reference frame of the planet, the spacecraft's speed relative to the planet is the same before and after the flyby. But from the Sun's reference frame, the spacecraft's speed has changed because the planet itself is moving. Voyager 1's flyby of Jupiter in 1979 added roughly 15 kilometers per second to its speed relative to the Sun. The subsequent flyby of Saturn in 1980 added further velocity. These additions, superimposed on the initial velocity from the launch rocket, combined to give Voyager 1 a speed sufficient to escape the solar system entirely and continue outward indefinitely. Without the gravitational assists from Jupiter and Saturn, Voyager 1 would have had to carry vastly more fuel to achieve the same trajectory, adding mass that would have been prohibitive given the technology of the era, or would have simply been too slow to reach its current position in any human-relevant time frame. The elegance of gravitational assist is that it extracts energy from planetary motion, that ancient reservoir of kinetic energy built up over billions of years of orbital dynamics without depleting it in any measurable way. The planet Jupiter loses a tiny, essentially undetectable amount of energy from each spacecraft that swings around it, while the spacecraft gains an enormous mission-determining boost. The transaction is thermodynamically legitimate, governed by conservation of momentum and energy, but it feels almost illicit, borrowing from the immense wealth of the solar system's gravitational architecture without asking permission or paying interest. The launch itself, the specific act of sending Voyager 1 into space from Earth in September 1977, is a moment worth dwelling on, because it sits at the boundary between all the preparation that preceded it and all the discovery that followed it, and because the people who witnessed it understood they were watching something genuinely unprecedented. The rocket that carried Voyager 1 was a Titan IIIe with a Centaur upper stage, a launch vehicle capable of delivering substantial payloads to high-energy trajectories. The launch from Cape Canaveral was planned with meticulous precision because the trajectory to Jupiter required the spacecraft to be inserted into a very specific path at a very specific velocity at a very specific time. The gravitational assist calculations that would carry Voyager 1 from Jupiter to Saturn and then outward into the heliosphere depended on the launch being correct to a degree of precision that, in 1977, was at the very edge of what the technology of the era could provide. The launch succeeded. Voyager 1 separated from its upper stage and began the outward journey that has not ended since and will not end as long as the universe exists in anything like its current form. What the people who watched the launch could not have known was how long the mission would actually last, how far the spacecraft would actually go, or what it would actually discover. The outer solar system in 1977 was largely unknown territory. Jupiter had been visited by Pioneer 10 and 11, but only briefly and with less sophisticated instruments. The moons of Jupiter and Saturn were barely resolved from Earth-based telescopes. The rings of Saturn, while known to exist, were understood at nothing like the level of detail that Voyager would reveal. The possibility of active volcanoes on Io, of liquid water oceans under the ice of Europa, of the extraordinarily complex ring structure of Saturn, all of these were either not anticipated or anticipated only in the most tentative and theoretical terms. The people who launched Voyager 1 were sending it into genuine darkness, in the sense that they could not clearly see what it would find there. The instruments they placed on it were their best guesses about what would be scientifically useful at each world the spacecraft would visit. The trajectory was calculated with extraordinary care, but also with the awareness that orbital mechanics models of that era had genuine uncertainties. The mission was a leap of extraordinary ambition and extraordinary preparation, and also an acknowledgement that preparation could only go so far, that the universe would reveal what it revealed when the instruments were actually there. There is something worth exploring carefully about the relationship between Voyager 1 and the specific cultural and political moment of the late 1970s when it was built and launched, because the mission did not emerge from a vacuum. It emerged from a specific historical context that shaped what it was and what it was expected to accomplish. The late 1970s in the United States were a period of significant cultural and political turbulence. The Vietnam War had ended badly a few years earlier. Watergate had destabilized public trust in institutions. Economic pressures, including the energy crisis and significant inflation, were straining public confidence. The optimism of the 1960s, which had fueled the Apollo program, and the broader sense that human ingenuity could accomplish anything it set out to do, had taken substantial hits. The space program itself was in transition. Apollo had ended in 1972, and the resources and attention that had sustained it were no longer available. NASA's budget was declining relative to its Apollo-era peaks. The space shuttle, still years away from its first flight, was being developed as a cheaper and more routine way to access space. The sense of grand, outward-reaching ambition that had characterized the Apollo era was giving way to something more modest and more routine. Against this backdrop, the Voyager mission represented a different kind of ambition, not the planted flag of a national competition, but the outward reaching of scientific curiosity, not the dramatic human presence of astronauts, but the quiet, patient, autonomous capability of an unmanned spacecraft that would keep working long after its creators had moved on to other things. The planetary encounters, when they came, were celebrated widely and produced a genuine sense of collective human achievement that transcended the political difficulties of the era. The images of Jupiter's swirling atmosphere and Io's volcanic plumes and Saturn's intricate rings arriving from instruments a billion kilometers away reminded a distracted and somewhat disheartened public of what scientific ambition could produce. Carl Sagan's role in communicating this to the public was crucial. His ability to explain the significance of what Voyager was finding, to translate the technical results into terms that captured the imagination and the emotion of a general audience, was unusual in a scientific culture that often prioritized internal communication over public engagement. Sagan made the Voyager discoveries feel like what they were: genuinely extraordinary revelations about the nature of the solar system and, by extension, about the nature of the universe. The Golden Record was part of this communication strategy, as well as being a genuine act of cosmic outreach. By placing the record on the spacecraft, Sagan and his colleagues gave the broader public a point of personal and emotional engagement with the mission that went beyond the technical results. The idea that humanity was sending its music and its voices and its sounds into the cosmos in this small, golden object attached to a spacecraft heading into the dark was something that anyone could understand and feel connected to, regardless of whether they understood the science of plasma oscillations or the dynamics of gravitational assists. Let's think now about Voyager 1 in relation to the broader history of human exploration and what it tells us about how we understand the concept of going somewhere, because the Voyager mission represents a fundamentally different kind of exploration from anything that preceded it. Throughout human history, exploration has meant something specific: a person or people going somewhere, experiencing it directly, returning with knowledge, and perhaps with physical samples and artifacts, and using that experience to expand the understanding of both the explorers and the civilization they represent. The Great Sea Voyages, the polar expeditions, the mountain expeditions all involved human beings physically present in new environments, experiencing those environments with their senses, making decisions on the spot in response to conditions that could not be fully anticipated, and then, in most successful cases, returning to tell what they had found. Robotic exploration, which is what Voyager 1 represents, is something different in kind, not merely in degree. No human being has been to Jupiter or Saturn or to the heliopause or to interstellar space. No human being has directly experienced the color of Jupiter's clouds or the texture of Io's volcanic landscape or the specific quality of the darkness beyond the heliosphere. Everything we know about these environments comes through the mediation of instruments, sensors, that convert the properties of distant environments into electrical signals that can be transmitted back to Earth and converted there into images and data that scientists and engineers and eventually the broader public can work with. This mediated experience is real in the sense that the instruments accurately measure what they measure and the data faithfully represents the conditions at the spacecraft's location. But it is also indirect in the sense that no one has stood on Io and watched a volcanic eruption from a few kilometers away. No one has floated at the heliopause and felt the transition from heliospheric particle environment to interstellar particle environment with their body. The exploration is genuine, but the experience is vicarious. What Voyager 1 has produced is something that might be called vicarious discovery, the extension of human curiosity and human knowledge into environments that human beings have not, and in many cases cannot directly inhabit, through the mediation of instruments that serve as prosthetic senses, extending our perception across distances that our bodies cannot bridge. This kind of exploration is not lesser than the physical exploration of previous eras. It is different, adapted to a universe in which the scales of distance are so vast that physical presence is, in most cases, simply not available. The astronauts who have traveled to space have done so at the farthest, to the Moon, roughly 384,000 kilometers from Earth. Voyager 1 is currently more than 60,000 times farther than that. The physical presence that characterized all previous exploration is simply not available at these scales, and Voyager 1 represents the development of a different but genuine mode of exploration that is adapted to the actual scales of the solar system and beyond. The specific instruments aboard Voyager 1 that are still functioning in the mid-2020s deserve careful attention because they are what makes the mission scientifically alive in the present rather than simply historically significant, and because understanding what they measure and why it matters reveals the ongoing value of a mission that many people assume has long since completed its work. The plasma wave subsystem, one of the instruments still returning useful data, detects electric and magnetic field oscillations in the surrounding medium at frequencies between a few hertz and tens of kilohertz. These oscillations, produced by disturbances in the plasma environment through which the spacecraft is moving, can be converted to audio by playing the relevant frequencies through a speaker, and the sounds that result, plasma waves from interstellar space converted to audible frequencies, have been released publicly by the Voyager team and are genuinely extraordinary to hear. They sound like nothing so much as distant, abstract whale song, which is perhaps not entirely surprising given that plasma oscillations and acoustic oscillations share some mathematical structure, even though the underlying physical processes are entirely different. The cosmic ray subsystem measures the energy spectrum and composition of charged particles arriving from outside the solar system. This instrument has been fundamental to establishing that Voyager 1 has crossed the heliopause, since the composition and energy distribution of the particles changed dramatically at the boundary in the way that models predicted. The data continues to accumulate as the spacecraft moves through the local interstellar medium, building a record of how the cosmic ray environment changes with distance from the heliopause. The low-energy charged particle instrument measures particles with lower energies than the cosmic ray subsystem, including the very low-energy particles that are associated with the solar wind and its interactions with the surrounding medium. This instrument has contributed significantly to understanding the complex structure of the heliosheath, the turbulent region between the termination shock and the heliopause. The magnetometer on Voyager 1, which measures the local magnetic field, has been providing data about the orientation and intensity of the interstellar magnetic field in the region through which the spacecraft is traveling. The measurements have been somewhat more difficult to interpret in recent years as the power available to the instrument has declined, but they continue to provide information that no other instrument can provide. Each of these instruments was designed and built in the early 1970s using the best technology available at the time, with an expected operational lifetime of perhaps 5 years, the duration of the primary mission through Jupiter and Saturn. They are now approaching 5 decades of operation, in conditions that were not anticipated when they were built, in an environment that their designers had only theoretical models of. That they continue to function is a testament to the engineering of the team that built them and to the particular chemistry of luck and care that has sustained the mission through circumstances that could easily have ended it multiple times. One of the most poignant aspects of the Voyager 1 story, and one that is not always highlighted in accounts of the mission, is what the experience has been like for the people who have spent the most time with it. Ed Stone, who joined the Voyager team as project scientist in 1972, 5 years before the launch, and who remained the primary public voice of the mission for several decades, has described in various interviews the experience of following Voyager 1 across the solar system and eventually into interstellar space as one that has continuously exceeded his expectations. He has said that at each stage of the mission, the assumption was that the interesting science was mostly behind them, that the next phase would be quieter and less revelatory, and that at each stage this assumption was proved wrong by new discoveries. The heliopause crossing was, by his account, one of the most scientifically significant moments of his career, even though it occurred more than 40 years after he joined the project. The particle environment changed in the ways the models had predicted, but the magnetic field orientation was wrong in ways that required serious rethinking of how the heliosphere interacts with the local interstellar medium. The surprise, the revision of models, the discovery of something genuinely new, came not from the glamorous planet encounters of the 1970s and 1980s, but from the patient, quiet, long-sustained journey of a spacecraft that had been traveling for 35 years before revealing this particular secret. This trajectory, from the immediate excitement of launch and the planetary encounters to the long, quiet cruise phase to the eventual crossing of a fundamental boundary and the discovery of new science at the edge of the known world, has a structure that is less like a conventional adventure story and more like something else. A kind of devotion, perhaps. A commitment to paying attention over such a long period that the thing you are paying attention to eventually shows you something that impatience would never have revealed. The Voyager team is, in this sense, an unusual model of what sustained scientific attention can produce. They have followed a spacecraft for longer than many of them have been professionally active, through periods when the mission seemed to be winding down, through budget pressures and competing priorities, through the losses of colleagues who began the work with them and did not live to see the heliopause crossing, through the gradual difficult management of declining power and failing systems. And the mission has rewarded that attention with discoveries that could not have been anticipated and could not have been obtained any other way. Let's consider the specific and somewhat haunting question of what Voyager 1 is doing right now, in this exact moment as you are reading or listening to this. It is moving. It has been moving continuously since September 5th, 1977, without ever stopping, without ever slowing significantly, without ever ceasing its outward journey. Right now, at this moment, it is covering approximately 17 kilometers of new interstellar space that no human instrument has ever traversed before. In the time it takes to read one sentence of this script, Voyager 1 has moved roughly 200 or 300 kilometers farther into the interstellar medium. It is transmitting. Assuming the transmitter continues to function, it is right now sending a faint radio signal back toward the solar system, carrying data from its remaining instruments, reporting on the particle environment and the magnetic field, and whatever the plasma wave system is detecting in the local interstellar medium. That signal, traveling at the speed of light, will reach Earth in slightly over 22 hours. The people monitoring Voyager at the Jet Propulsion Laboratory will receive it, decode it, archive it, and analyze it. And then, in some form or another, that information will become part of the accumulated human knowledge of what the interstellar medium is like in the specific region that Voyager 1 is passing through right now. It is cold. The temperature of the spacecraft's exterior is determined by the balance between the heat radiated by the RTG, distributed through the spacecraft via conduction and the internal heating elements, and the heat lost to radiation into the surrounding environment. In the absence of any significant external heat source, the equilibrium temperature is very cold, though precise measurements of the spacecraft's external temperature are not directly available from the instruments that remain operational. It is dark. The sun, which powers every human activity that has ever occurred or that currently occurs, appears from Voyager 1's position as a very bright star, the brightest in the local sky by an enormous margin, but not a sun in the sense of filling the sky with light and warmth. It is a point, intense and specific, at a distance that makes it cold rather than warming. And it is alone. There is no other object of human origin within any remotely comparable distance of Voyager 1. The nearest human-made object is Voyager 2, which is traveling in a different direction and is currently somewhat closer to the Sun, but still billions of kilometers from Earth and billions of kilometers from Voyager 1. Beyond these two spacecraft, the universe in every direction that matters is empty of human presence. The word alone is somewhat strange to apply to a machine, since machines do not experience loneliness. But the specific configuration of Voyager 1 in the universe, the single human object in an otherwise unoccupied immensity, has a quality that the word alone does capture in some important sense. It is what human presence looks like at the very edge of where human presence has reached. It is the leading edge of our exploration, a tiny point of organized matter moving through the vast disorganization of the cosmos, faithfully transmitting its signals homeward. Let's think about Voyager 1 in relation to the cosmic microwave background, the oldest light in the universe, which we have explored in detail in previous episodes and which has a specific connection to the Voyager story that is worth drawing out. The cosmic microwave background, the ancient glow of the Big Bang, permeates all of space. It fills every cubic centimeter of the universe, including the cubic centimeter currently occupied by Voyager 1 in interstellar space. The spacecraft is immersed in this 2.7 Kelvin radiation field just as everything else in the universe is. And the instruments aboard the spacecraft are continuously bathed in photons that have been traveling through the universe since 380,000 years after the Big Bang. The specific temperature of the cosmic microwave background, 2.7 Kelvin, represents the floor below which the radiation environment of deep space cannot fall through radiative cooling alone. Any object in deep space that is isolated from all other heat sources will cool toward this 2.7 Kelvin background through radiation, but will never cool below it, because the background itself continuously supplies a tiny trickle of energy to anything it can reach, which is everything. Voyager 1 is far above this temperature limit because of the heat supplied by its RTG. The spacecraft's interior, maintained at operational temperatures by heaters powered by the RTG, is far warmer than the cosmic background. But as the RTG's output continues to decline, and as the heaters are progressively shut down to save power, the spacecraft will gradually cool toward the background temperature, a process that will accelerate after the transmitter fails and all power is no longer used for spacecraft operation. Eventually, after the RTG has decayed sufficiently and all heaters have failed, the spacecraft will equilibrate thermally with its environment. Its temperature will settle toward the cosmic microwave background temperature, warmed slightly by the absorption of radiation from the Sun and other nearby stars, but primarily at the temperature that the universe itself provides, roughly 2.7 Kelvin above absolute zero, or approximately minus 270 degrees Celsius. This is the temperature at which Voyager 1 will drift through the galaxy for the rest of its existence, as cold as the universe requires anything isolated in deep space to eventually become, but not colder, maintained at this specific temperature by the faint glow of the oldest light there is. There is something quietly wonderful about this connection, the spacecraft that carries the sounds of Earth eventually cooling to the temperature of the Big Bang, maintained at that temperature by the same ancient light that allows us to study the earliest history of the universe. The most human artifact in interstellar space, resting at last in the ambient warmth of creation itself. There is a specific and interesting aspect of Voyager 1's trajectory that connects it to the broader structure of the solar system in a way that is not always discussed, and it concerns the fact that Voyager 1 did not simply fly straight outward from the Sun, but followed a trajectory that was shaped by the specific flyby geometry of Jupiter and Saturn in ways that created a particular exit angle from the solar system. The gravitational assists from Jupiter and Saturn did not merely speed up Voyager 1, they also redirected it. Each flyby bent the spacecraft's trajectory, changing not only its speed but its direction, and the combined effect of the two encounters was to send Voyager 1 outward at a specific angle relative to the ecliptic plane, the flat disk in which the planets orbit. Voyager 1 is heading out of the solar system at an angle of roughly 35 degrees above the ecliptic plane, in the direction of the constellation Ophiuchus in the sky as seen from Earth. This specific exit angle was determined by the geometry of the Jupiter and Saturn flybys, which in turn was determined by the specific positions of those planets in 1979 and 1980 when the flybys occurred, which was in turn determined by the grand tour opportunity that had been identified in the late 1960s. This chain of determinations, reaching from the orbital mechanics of the outer solar system billions of years before Voyager was built, through the decision to pursue the grand tour opportunity, through the specific launch window chosen for Voyager 1, through the trajectory geometry of each planetary flyby, all the way to the specific direction in which Voyager 1 is now drifting through interstellar space, illustrates something important about how even seemingly small choices in a trajectory can have consequences that propagate across very long timescales and very large distances. The direction in which Voyager 1 is heading is not the direction a mission planner would have chosen if the sole goal had been to exit the solar system in the most scientifically interesting direction or the direction of the nearest star. It is the direction that resulted from the combination of constraints, the available gravitational assists, the scientific priorities that led to the Titan flyby, the launch window and trajectory options of 1977. The eternal drift is in this specific direction because of all these specific decisions, and the irreversibility of the trajectory means that none of those decisions can now be revisited. This is true of most of the important decisions in history. They were made under the constraints of specific circumstances, and their long-term consequences were shaped by those circumstances in ways that the decision-makers could not fully anticipate. The people who designed the Voyager trajectory were working with the solar system as it was, and the technology as it existed, and the scientific priorities as they were understood, and the result was a trajectory that no one could have fully predicted in advance, heading in a direction that was determined as much by circumstance as by intention. The eternal drift of Voyager 1 is, in this sense, a product of the whole complex history that produced it, from the formation of the solar system to the development of the space program to the specific decisions made by specific people in the 1970s. It carries that history with it, encoded in its velocity and its direction, as surely as the golden record carries the music and voices of 1977. Let's spend some time now with a particular and quietly extraordinary aspect of the Voyager story that connects it to the broader history of science and to the specific way that scientific knowledge grows through the combination of theoretical prediction and experimental confirmation. When Voyager 1 was designed in the early 1970s, very little was known about most of the environments it would encounter. Jupiter had been observed from Earth and from Pioneer 10 and 11, but the outer solar system beyond Jupiter was largely uncharted. The structure of the heliosphere was known theoretically, but had never been directly measured from the inside at any great distance from the Sun. The interstellar medium was observable from Earth through its effects on electromagnetic radiation passing through it, but its specific properties at any given location could only be inferred, not directly measured. The predictions that theorists made about these environments before Voyager arrived were a mixture of the correct, the partially correct, and the wrong. Some aspects of Jupiter's atmosphere behaved roughly as expected. Others were dramatically different. The discovery of active volcanism on Io was essentially unpredicted, though one theoretical paper published just before the Voyager flyby had speculated that tidal heating might produce volcanic activity, a prediction vindicated to an extraordinary degree by the images returned. The ring system of Saturn was broadly anticipated, but its specific complexity was not. The structure of the heliosphere was partially correct in theory, but wrong in specific ways that only direct measurement could reveal. This is the normal pattern of science. Theory does its best to predict what observation will find, and observation returns, confirming some predictions and overturning others, adding information that theory then absorbs and uses to make better predictions for the next round of observation. The Voyager mission was, among other things, a very large-scale version of this process, providing direct observations of environments that theory had predicted with varying degrees of accuracy and that subsequent theory has incorporated into much more sophisticated models. The specific surprises that Voyager 1 has produced over its decades of operation, from the volcanism on Io to the complexity of Saturn's rings to the orientation of the interstellar magnetic field at the heliopause, are all examples of what scientists sometimes call the universe's tendency to be more interesting than we expected. Not wrong in the sense of being inaccessible to scientific understanding, but more complex, more structured, more specific in its character than the simplified models that theorists inevitably construct when direct data is unavailable. Every discovery that Voyager 1 has made has been a reminder that the universe has more structure, more specificity, more surprises than the best available model predicted, and that the way to find out what the universe is actually like in any given place is to go there and look. As we approach the final moments of tonight's exploration, let's consider the specific question of what Voyager 1's eternal drift means for the future of our relationship to it, after the transmitter falls silent. When the last signal from Voyager 1 arrives at Earth, there will be no dramatic event to mark the moment. No explosion, no visible disappearance. The signal will simply become too faint to detect against the background noise, and then the science instruments will shut down from lack of power, and then the transmitter itself will no longer function. The last data will be archived and analyzed, and then there will be silence where before there was signal, and Voyager 1 will complete its transition from an active mission to a monument. The transition to monument status does not diminish what the mission has accomplished. Every kilogram of data archived from the mission is real knowledge about the solar system and the interstellar medium, knowledge that will remain valuable for as long as scientists continue to study these environments. The long record of measurements from the journey through the outer solar system, through the heliosphere, and into interstellar space represents a dataset that is literally irreplaceable because the specific positions and the specific times at which the measurements were made can never be replicated. But there is something different about the period after the signal stops, something worth being honest about rather than papering over with scientific completeness. The specific texture of the relationship between Voyager 1 and Earth changes. During the active mission, there is an ongoing dialogue, however one-sided and however delayed. The spacecraft sends data. We receive it, analyze it, send commands, receive more data. The relationship has the character of a continuing conversation. After the signal stops, that conversation ends. The spacecraft continues on its trajectory, completely indifferent to whether anyone on Earth is thinking about it, completely unaware of any changes in the civilization that built it, completely unaffected by whatever happens to the solar system over the billions of years of its journey. It becomes, in a very real sense, past. It becomes history. The relationship between Voyager 1 and humanity becomes the relationship between any historical artifact and the people who study it. A one-directional relationship in which the artifact is fixed and the people continue to change and grow and eventually, in some future form, cease to exist. There is a specific quality to the thought of a machine that will continue moving after every trace of its creators is gone. Not sorrowful, exactly. Not triumphant. Something quieter than either. The sense of something human extended beyond the human, carried outward by the physics that governs everything, belonging now to a future that we cannot inhabit or predict or control. The message in a bottle, floating on a sea that has no shore it is heading toward. One more thread to pull before we let the night settle. The Voyager mission has been described, by many people over many years, as one of the greatest achievements of the human species. This is not hyperbole, and understanding why it deserves this description requires thinking about what the word achievement actually means in this context. An achievement is not merely something that is technically difficult. Many things are technically difficult without being genuinely significant. An achievement is something that changes what is possible, what is known, or what can be imagined in a way that matters beyond the immediate practical value of the thing accomplished. By this standard, the Voyager mission is genuinely, historically significant in multiple ways. It changed what we knew about the outer solar system in specific, detailed, irreversible ways. The solar system as it is understood after Voyager is fundamentally different from the solar system as it was understood before. The discovery of active volcanism on Io changed our understanding of the energy sources available to planetary bodies. The discovery of complex ring structures changed our understanding of how gravity and orbits interact in particulate systems. The evidence for subsurface oceans on Europa changed our assessment of where in the solar system life might plausibly exist. These are not incremental improvements to existing knowledge. They are qualitative changes in the kind of picture we have of our planetary neighborhood. It extended the reach of human presence, in the sense of human instruments and human curiosity, to regions of space that no human-made object had ever entered. The heliopause crossing was, as we discussed, a physical crossing of a real boundary, the actual outer edge of the Sun's direct influence, and no other human artifact has ever crossed this boundary except the Voyager spacecraft and their pioneer predecessors. And it demonstrated, through the golden record, that human exploration could be motivated by something beyond the practical and the competitive, by something as seemingly impractical as the desire to communicate with whatever else might exist in the universe, to extend the reach of human expression into the cosmos without expectation of immediate return. This demonstration, this proof that the human species is capable of this kind of reaching beyond the practical, is itself an achievement in the full sense of the word. The Voyager mission is a great human achievement, not because it was the first to do what it did, though it was. Not only because it was technically difficult, though it was extraordinarily so, but because it extended the boundaries of what humanity has done, what we have known, and what we have proven ourselves capable of imagining in ways that matter far beyond the immediate scientific results. And Voyager 1 carries that achievement outward, forever, in the dark, at 17 kilometers per second, faithful to the trajectory that physics gave it and to the mission that its creators sent it on. It is the most distant evidence of what we have accomplished and what we have reached toward. It is, right now, somewhere in the interstellar medium, moving, transmitting, carrying the sounds of Earth into a silence that will last essentially forever. That is, by any measure, something extraordinary. One last thought before the night finally settles. There is a specific kind of hope embedded in the golden record, one that is easy to miss if you think about it only in terms of the probability of detection. The hope is not primarily about being found. The hope is about the kind of being that finds things worth sending, about the species that, faced with the opportunity to send something into the cosmos, chose to put music on it. A civilization that chooses to put music on an interstellar spacecraft has decided something specific about what matters. Not efficiency, not self-interest, not the maximum information content per kilogram of mass. Music. The specific, irreducible, non-transferable experience of human beings moving sound through air in patterns that produce something that other human beings recognize as beautiful or sad or joyful or sublime. This experience cannot be explained to someone who has never had it. It can only be transmitted in the hope that the being on the other end has, in its own way, its own equivalent, something that cannot be explained but can only be heard. The Golden Record is not primarily a scientific document, though it contains scientific information. It is primarily an act of faith, in the specific and secular sense that faith sometimes means the extension of care and attention towards something that may never respond, in the knowledge that the extension of that care and attention is its own justification. Voyager 1 carries this faith outward into the dark at 17 kilometers per second. It has been carrying it for more than 4 decades. It will carry it in silence after the transmitter finally fails for billions of years beyond that. The machine will persist long after the civilization that built it has transformed into something unrecognizable, carrying what was most human about that civilization's moment of reaching, preserved in gold and copper and aluminum at approximately 2.7 Kelvin in the interstellar dark. That is why Voyager 1 will drift forever. Not as a tragedy, not as a failure, but as the permanent physical expression of a choice made by a species at a specific moment in its history to reach beyond what it could reach, toward what it could imagine, and to carry in that reaching the most particular and the most universal things it knew how to express. Beyond the cosmos will be here whenever curiosity calls you back to sit with another of the universe's great questions. There is always more to explore, and always here a calm, quiet space to do it. For now, let the signal continue its journey across 22 light hours of space. Let the machine drift. Let the Golden Record carry its cargo of music and voices and rain and wails toward whatever the universe contains. Let your breathing slow. Before the silence fully settles, there is one more dimension of the Voyager story worth sitting with. One that concerns the specific experience of receiving a signal from beyond the solar system and what that means for the people who dedicate their working lives to interpreting it. The Deep Space Network antenna that receives the signal from Voyager 1 is, at the moment of reception, picking up a transmission that left the spacecraft more than 22 hours ago. The antenna dish, tens of meters in diameter and exquisitely sensitive, has to be pointed with extraordinary precision at the tiny patch of sky that corresponds to Voyager 1's current position, accounting for the fact that the spacecraft is moving and the Earth is rotating and the signal is arriving from an angle that changes continuously. The act of pointing the antenna and acquiring the signal is itself a piece of applied engineering that represents decades of refinement. The signal that arrives is so faint, carrying so little power, that distinguishing it from the ambient noise in the radio frequency environment requires signal processing techniques that were not available when Voyager 1 was launched, and that have been steadily improved over the decades since. Every generation of digital signal processing technology that has been developed for other purposes has, in some form, been applied to the task of squeezing more information out of the faint signal from the most distant transmitter in human history. When the data is finally decoded and displayed, what the operators see is a stream of numbers representing the current state of Voyager 1's systems, the output voltages of its power sources, the temperatures of its various components, the readings from its science instruments. These numbers, arriving across more than 22 hours of travel time, represent the state of the spacecraft as it was 22 hours ago, in a region of space that no one on Earth can see directly and that no other instrument can measure. There is a specific practice that has developed over decades at the JPL Operations Center, the practice of treating the data that arrives from Voyager 1 as something genuinely precious, to be archived with care and analyzed with patience, because the possibility of ever replacing this data, of ever sending another instrument to this specific location to collect it again, is essentially zero. The data is not replaceable. The measurements are not repeatable. The interstellar medium at the specific location of Voyager 1 in the specific year that Voyager 1 is passing through it will never be directly measured again by any human instrument. This awareness of irreplaceability shapes the entire relationship between the mission team and the data. Every anomaly, every gap in the telemetry, every period when the signal was too weak to be correctly decoded represents a permanent loss of information that no future instrument can recover. The team treats the data with a care that is driven not by institutional requirement, but by the genuine understanding that what they have in their hands is unique, and that handling it with anything less than the utmost care would be a form of loss. Let's close with the very longest view possible, the one that places Voyager 1 against the full arc of cosmic time, from the formation of the universe to its eventual fate, and asks what it means that in this narrow window, on this small planet, in this ordinary solar system, something like Voyager 1 was made. The universe is approximately 13.8 billion years old. It will continue to exist in various forms for timescales that are essentially beyond comprehension. In trillions of years, the current era of star formation will be over. In quadrillions of years, the last stars will have burned out. In timescales that can only be written in scientific notation, even the protons that make up ordinary matter may have decayed. Eventually, black holes will evaporate through Hawking radiation, and what remains of the universe will be an extraordinarily thin, cold, dark fog of the simplest possible particles, spread across an expanse so enormous that the observable universe of today would look like a single atom in comparison. Against this backdrop, the 13.8 billion years that have already passed represent only the beginning. The universe in its current, star-bright, galaxy-rich, structure-filled phase is, from the perspective of the very long future, a brief and extraordinary episode, a moment of concentration and structure that will eventually dissolve into the maximal entropy of the far future. And within this brief and extraordinary episode, on a planet in an ordinary solar system in an ordinary galaxy, a species of hominid, remarkable primarily for its large brain and its extraordinary capacity for curiosity and communication, developed the technology and the will to build a machine and send it outward into the dark. And that machine is still moving, still transmitting, still faithfully carrying its cargo of human expression and scientific measurement outward into the interstellar medium toward a future that no human eye will ever see. The machine will outlast the species that built it. It will outlast the planet it came from. It will outlast the star that warmed the planet. It will outlast, very probably, the galaxy that contained the star. It is, in this sense, one of the most durable things that human civilization has ever produced, not because it was engineered for durability, which it was not, but because the environment it is moving through is so empty and so free from the forces that destroy things that it will simply persist, inert and cold and silent, for timescales that exceed the imagination. This thought, when held fully, is genuinely extraordinary. Not because Voyager 1 is the most technologically sophisticated thing we have ever made, which it is not. Not because it represents our greatest scientific achievement, which is debatable, but because it represents something about the human capacity for reaching beyond the practical and the immediate, for extending care and curiosity toward a future and a universe that will not remember us, and doing so with such thoroughness and such genuine feeling that the record of that reaching will persist in the universe essentially forever. We were here. We made this. We put music on it, and we sent it into the dark. That is enough. That is genuinely more than enough. There is one final image worth holding before tonight's exploration truly closes. Somewhere, right now, in the offices of the Jet Propulsion Laboratory in Pasadena, California, someone is watching a monitor that displays data from Voyager 1. The numbers on the screen represent the current state of a machine that has been traveling for nearly 5 decades in a region of space that exists beyond the edge of the solar system, transmitting measurements that no other instrument will ever be in a position to make. The person looking at those numbers may have been doing this work for years, or may be newer to the team, inheriting a tradition of watchfulness and care from the scientists and engineers who came before them. Outside the window of that office, the ordinary world goes on. Traffic moves. Seasons change. Conversations happen about things that have nothing to do with interstellar space. And above all of it, invisible against the daytime sky, a signal is arriving from 22 hours away, from a machine the size of a small car drifting through the interstellar medium at 17 kilometers per second, carrying the sounds of whales and the brainwaves of someone in love, and the music of Beethoven and the laughter of children, outward and outward and outward, without end. Rest now. The drift continues. The signal, for a while longer, holds. Good night.